Great.
So now the first speaker is the keynote section by Yadunund Vijay. Yadunund is a robotics software engineer at Intrinsic and one of the main developers of the Open-RMF, the open source software for managing fleets of robots.
And today Yadu is going to talk about how we can build a multi-fleet simulation with OpenRMF, so we can practice, we can develop our programs with OpenRMF by using those simulations, and then we can transfer later to the real robots. So welcome to the conference. Yadunund, are you ready? Hello? It looks like I cannot hear you. I don't know. Looks like you are ready. Then, okay, so I cannot hear you now, but you can go ahead. The audience can hear you.
Sorry, Ricardo. Are you addressing me?
Yes, and now I can hear you. Okay, great,
perfect.
Excellent.
Sorry, I was on mute.
Go for it.
All right. Thank you, Ricardo. Good morning, good afternoon, everyone. My name is Yadunund. I go by Yadu for short. And I'm a software engineer at Intrinsic and formerly Open Robotics. And today it's my pleasure to go over this short workshop on OpenRMF, and specifically how you can use OpenRMF to quickly configure 3D simulation environments for multi-fleet simulations. So let's jump right in. So for today's session, it's pretty short. It's about 1 hour. And I should say about 40 minutes with some questions. And what we'll do is we'll go over what OpenRMF is, some of the concepts that make it suitable for multi-fleet orchestration. And then we'll spend some time on Traffic Editor today. So that's the main focus. Specifically, we'll look at how can we use this tool that is provided within OpenRMF to quickly construct 3D simulation environments. So this deck or this workshop is borrowed from a workshop that we did at ROScon Kyoto last year. But for the purpose of this session, we'll be following an abridged version of it. So let's jump in. As you may know, OSRF, or Open Source Robotics Foundation, primarily develops, distributes, and maintains 3 large pieces of open source software. ROS, you're all familiar with this. It's one of the world's most widely used SDK for building robot applications. We also develop and maintain Gazebo Classic, and the new Gazebo now. And this is a modular, configurable physics-based simulator where you can simulate your robot applications prior to deployment in the real world. And so recently, over the past few years, we've been developing something called OpenRMF, or the Open Robotics Middleware Framework. And OpenRMF is what, if you think of ROS helps you build a single robot, helps you get information from sensors, and has all these algorithms for you to perform complex activities using your robots. OpenRMF is sort of the ROS that's intended for use across different robots. And the goal here is to bring in intelligence to coordinate multiple brands of robots within the same facility. We'll talk a bit more about why this is required in the next few slides. All right, so increasingly, we're asking a lot more from robotics or robots within facilities. So before, it used to be the case that robots were used in very specialized environments like manufacturing facilities, or maybe inside semiconductor storage equipment centers. And there wasn't much interaction with people or other types of robots. But this has been changing over time. So we're seeing facilities increasingly adopting more and more robotic automation. And they're not just interested in a single type of robot. They're very interested in deploying multiple types of robots that perform different activities. So you may have a robot within a facility that's doing cleaning. So that's an increasingly popular application these days. Robots are scrubbing floors or vacuuming surfaces. But at the same time, you may want to have robots that do deliveries. So if you're a hospital, for example, you want to move equipment from one room to another, you could be using robots to do this. Or you may be using robots for patrolling purposes. So intrinsically, there is this need to have multiple robots occupy the same space. But there are some challenges that we have seen from this approach. Fundamentally, robots don't communicate with each other. And this is not a problem with the robot themselves, but it's rather a consequence of how robots are developed. So each vendor typically develops their robot using their own protocols, using their own messaging standards. So the way you talk to one type of robot fleet is not the same as you talk to another different robot fleet. So they're not conveying their intentions in the same standard format. And that leads to a lot of problems, right? Specifically, one big problem we've seen is sharing spaces. You may have a facility with narrow corridors or hallways, and typically when you have two or more robots coming down the same hallway, they're going to lead to a deadlock situation where one robot's trying to get around the other, but because the sensors pick up the other robot as simply an obstacle in space, the robot just ends up waiting indefinitely for the obstacle to clear. And this leads to a deadlock situation, or maybe the robots might dance around each other. If there's space in the hallway, they could kind of squeeze past, but it leads to certain inefficiencies. Moreover, we often require these robots to share infrastructure in the building, such as doors or lifts. We want robots to go through security doors or maybe take lifts to go to different levels and offices. And often the way this happens is the robot vendor will need to do a one-time integration of the door or the lift with their robot fleet. So they'll come down, they'll install their own equipment there so that their fleet can communicate with these systems. But this doesn't scale really well when you want to add several more robots to the system, right? So for fleet A, you have to do it once, for fleet B again, and so on and so forth. So the cost really scales for facility owners. And again, it brings in the problem of sharing these lifts. Can two robots from two different fleets use the same lift to go to a certain level, or does each fleet need to talk to the lift separately? So fundamentally, the problem is communication and, moreover, intelligent management of resources. So if I could summarize what OpenRMF is in a single sentence, it would be something like, it's a collection of tools and software libraries that allows robots or fleets to share resources effectively. And here, resources refers to space, such as hallways or floor area. It could refer to infrastructure equipment like doors and lifts, or other building automation systems in the facility. So this could be a conveyor system, some kind of vending machine, whatever it is. The core concept here is we want to be able to share resources among robots. And the OpenRMF ecosystem has a whole bunch of tools that's kind of summarized in this slide. So we have tools for traffic management. This is route planning and making sure robots get to where they need to go without having these deadlocks or other conflicts. We have task dispatch systems, and this allows this allows operators to kind of command these robots from a higher level. So you have a consolidated view of where all your robots are in, and you can also submit tasks, and RMF will take care of assigning these tasks to the right robot. So cleaning tasks will get assigned to a cleaning robot, and it will manage the execution of these tasks as well. And there's a whole bunch of other tools, but the focus for this session is going to be Traffic Editor, or RMF Traffic Editor. Before we get into that, a quick history of the OpenRMF project. So this project was started in Singapore in collaboration with several entities here, including hospital and government organizations. And since then, we've gone through several releases, and then we had our, as well as certain deployments here in Singapore and overseas. And we're sort of in a state right now where we're deploying OpenRMF in several other facilities within Singapore and also other parts of the world. So the point here is it's quite a matured platform at this point. All right, so a high-level overview of how RMF works. So it's a collection of nodes that communicate intentions to each other. So what we do is we standardize message formats for conveying intentions such as, this is where I want to go, this is the kind of equipment I want to use. And then we have these nodes that are able to perform some kind of intelligent logic on the information that they receive from the hardware itself. So we have core of OpenRMF. All of these nodes communicate via ROS2. And then depending on what sort of hardware you're talking to, you typically talk to a hardware through something called a adapter. And this adapter does the job of converting the robot or hardware-specific messages into the ROS2 formats that OpenRMF represents. So it's sort of the main translation point. So robots are integrated with OpenRMF through fleet adapters. You have doors through door adapters, lifts through lift adapters, and any other type of systems, we have other kinds of adapters as well. I'll just quickly talk about the market opportunities that OpenRMF creates. So it's not something just for people who develop robots or maybe people who are working in the robotics space, but it's also very beneficial for facility owners or operators who have requirements to integrate 2 or more robots in the same space. And it also provides them a great operational tool to consolidate their facility management systems within a same window, and you're able to look at the states of different systems. You're able to send requests out, so it kind of simplifies daily operations as well. And of course, it benefits robot vendor developers. You may be very good at developing your navigation system, but you're unsure of how to develop a fleet management system. You have tools in Open-RMF that you can leverage on to just build a fleet manager, or build maybe other sensor pipelines or other communication pipelines to talk to building systems. For infrastructure and solution providers, again, it provides a lot of APIs or building blocks that you can leverage on to quickly deploy robotic systems at scale in a facility. This is a quick overview of our collaborators. So we've integrated several different brands of robots with Open-RMF. We've deployed it at several sites and worked with several system integrators and hardware providers in connecting robot systems with building infrastructure systems. All right, so I'll just leave this in the slides, but this is just some information on starting points to get familiar with Open-RMF, and some tools you can leverage on to learn how it works internally. All right, so let's jump right in. So traffic editor, what is it and what are we going to do today? So when starting with any sort of robot deployment, especially with multiple fleets, it's important for us to define semantics. So semantics is a fancy way of just saying representing information, right? So we need to standardize the way we represent where robots can move, where their charging stations are, where they can park, what spaces they can roam around in, what spaces are off limits, etc. So traffic editor is sort of a tool that lets us annotate this information. And you'll see later on, we're working with 2D floor plans. And the goal is to add features to this floor plan to signify all of this information. But more importantly, we really emphasize on the value of simulation. So traffic editor also has a subset of tools that lets you quickly build 3D simulation environments. So today's focus will be sort of combining these two. We'll look at how we can quickly configure these 3D environments and then run some multi-fleet simulations within them. So at this point, I'm going to switch over to ROSject. And if you're following, I hope you're able to switch as well. And sorry, could I get a confirmation that you can see my ROSject before I proceed?
Yes, we can see your screen.
All right, perfect.
Everything is perfect. And you can close that notification. It's a question of the forum that appears.
All right.
There, okay.
Okay, so if everything's okay, let's go ahead. So in the ROSject, you should be able to see this notebook with some commands and information that we'll be going over together. So try to follow along as much as you can, but if not, the question box is always available for you to kind of ask questions along the way. And I'll just point out some other tooling we'll be leveraging here. So we'll be requiring to send commands through terminals. So if you look at the ROSject, the GUI, you should be able to see this terminal option here. And then, so I have a terminal open here, and let's just start from scratch here. So this is what it should be able to look like. So I believe with these two tools, we should be able to get through this workshop. And yeah, please feel free to ask questions along the way. So the first thing to do with Traffic Editor is to sort of open up a 2D floor plan. And we chose to work with 2D floor plans because it's typically what's available at most facilities. Increasingly, you're seeing 3D BIM information data that's also available. But typically for older sites, maybe you just have a floor plan of the floor or the building that you're interested in. And so one thing that we typically do is import the floor plan into Traffic Editor, and then we begin annotating it. So for the purpose of this workshop, you'll find the floor plan that we're using within this directory. So another tool you can open up is the code editor, although we may not have to use it much. There should be a workspace called RMF Workspace, and within the source folder, ROScon Workshop, ROScon Maps, you should see Workshop, and then this is where you'll find the 2D floor plan that we're going to start with. And there's an empty file that we'll be using to configure our site. So I'm going to jump back to our Jupyter notebook. You should see a command here that you can copy and run from your terminal. This should start Traffic Editor, but it also loads up a blank map for us. So I've copied that, and I'm going to go back to my terminal here and open up Traffic Editor. All right, so you should see a GUI window open up. I'm going to switch my tab here because I have it opened up separately. And during the course of this workshop, I'll be switching between the Jupyter Notebook as well as this GUI window. So hopefully you can see the floor plan here. And if I jump back to the Jupyter Notebook, so the first thing we need to do is create a level and then assign a floor plan to this level. I'm jumping back to Traffic Editor, and this is a step that we've already done. So if you're following along, this should already be done. And you can see the level is called L1. And just to give a quick overview of what you're seeing, this window here is the main canvas where you interact with the floor plan. We have a property toolbox here where we can edit our annotations. And here we have another dialog box to cycle through a few other features in Traffic Editor. So this is where we begin with. If you look at step 1, what we need to do is set a scale for the 2D floor plan. So right now we've just imported an image, and images have pixels in them. There's no way for the Traffic Editor to know what is the correlation between a pixel and meters, for example. So that's the first thing we do. So in order to do that, you should see a measurement icon here on the top toolbar. The short key is T. So if you click this measurement icon, you should be able to click at a starting point. You don't have to be super precise here. The point is to just have a good estimate of dimensions here. So I've created this measurement annotation here, and now I'm going to assign it a distance. And so this has to be in meters. So as you can see, my floor plan says that's about 12,000 millimeters, which is about 12 meters. And if you have other measurements in your floor plan, that's great. You can go on and add them, but we're just going to average it out. But I'd recommend choosing the largest distance you can, because that's going to help minimize all sort of errors that we see. So this distance is about 2.2 meters. And there we go. That's configured. So one limitation of this application right now is we have to save and reopen this in order to apply the scale. So let's go ahead and do that. I'm going to jump back to my terminal and then press Control-C to kill this program, and then hit the up arrow and run the same command again. If I jump back to my GUI, Traffic Editor should be loaded, and you should see that the scale has been applied now. So if you look at the scale value here, it's about 1 pixel corresponds to these many meters, so 0.0254, which is looking good. All right, so the next thing we're going to do is draw a floor. This is a floor polygon. So typically to run simulations, we need to have a ground plane. For those of you who've extensively ran gazebo simulations, you'll know that when you open gazebo, by default, it spawns a ground plane as well as a sun light source. So here we're going to define the ground plane for our simulation. So this is a pretty large room, and I'm just going to arbitrarily define a bounding area for the floor. So in order to do that, we need to create certain vertices, which will define the boundary of our floor. All right, so to do this, you should see this green circle icon here that says Add Vertex. The short key is V. So I'm going to create a vertex over here, maybe another one all the way out here. So again, you can do this however you'd like. I'm just arbitrarily bounding all the 2D space that I see here. Okay, so once I've defined all of these vertices, the next step is to draw the polygon itself. So again, in the toolbar, you should see this icon, Add Floor Polygon. The short key is F. So I'm going to click on that. And then now I'm just going to trace through the vertices that I've defined. So I should have mentioned this earlier, but to navigate through this canvas, you can use your mouse wheel to scroll for zooming in and out. And then if you hold your mouse button, you should be able to pan the window as well. So that's what I'm doing now. I'm kind of selecting all of these vertices to define a floor for my simulation. So once you're done, in order to exit from this tool, and this is really important, you need to right-click. So once you right-click, it's going to exit from the floor creation process. You should also be able to hit escape, but I recommend right-clicking. So now you should be able to select this floor, right? So that's the floor that we've created from these vertices. It's good to periodically save along the way. So you can hit Control S to do that. All right, so jumping into the ROSject. The next step after creating the floor polygon is to define walls. So this is something you'll see commonly at different sites. So you have floors, you have walls, you have doors, maybe lifts, and these are typically the features that we'll begin annotating. So I'm just going to roughly trace out where I think the walls are. You can take your time and be really precise with this, but for the purpose of this workshop, I am simply going to give a very rough outline of where I believe the internal walls are. All right, let's see. So maybe here, although the floor plan has a much larger perimeter, I'm going to cut it off here. Oops, apologies. There we go. And then I'm going to make sure I click off here. All right, and then you can press escape to exit the wall creation tool. And then if you want to move these vertices around, you can click on the move icon here in the toolbar, or short key is M. And then once you have that selected, you can click on a vertex and move that around as well. And then, for example, if I want this area to be closed off, I can create another set of walls here. I can just come in here and oops. There we go. All right, so this is really up to you, how long you want to spend making this site accurate. We had a talk that we gave recently on how you can actually use this to simplify mapping for robots that use SLAM for navigation. So you can use Traffic Editor to create a really high fidelity or a highly accurate representation of your 3D space, and then spawn a robot within the space and use your favorite SLAM software to create a map. And then you can even pass that map on to a real robot if your map is accurate enough. So for the purpose of this workshop, I'm going to be a bit quick about this process. So we have the floors and the walls ready. And let's see, what else can we add? So we can add some doors. So OpenRMF supports a few different type of door models. We have the hinge door, where there's a hinge on one of the vertices, and we swing or pivot about this vertex. We could also have double hinged, where you kind of have two doors that swing outwards or inwards. We have sliding doors that slide into the walls. And again, these can be of the single or double variant. And let's go ahead and try creating some of these doors. All right, so I'm going to click on this door icon here in the toolbar, add door, short key is D. And then I see a couple of doors here. So let me go ahead and add a door here. All right. So now you can see by default, it creates a single swing door. To change that to a double hinged, let's click on the line here that signifies the door. And then wherever you see typed, it says hinged here. Instead of hinged, let's change that to double hinged, double_hinged. When I do that, you can see that it switches to a double hinged door. And if I want to be really pedantic about this and match the floor plan, I can also do that. This ensures that the dimension of the door is the same as what's on the floor plan. If you'd like to change the direction of the swing, that's also something you can do. We have a motion direction property here. I believe if you change that to -1, it should flip the direction of swing. Here, I'm going to leave it at 1. to match whatever we have in the floor plan. I'm going to give this door a name. So by default, the name should say null. I'm just going to replace that with door 1. And then if you'd like, you can create another door as well. Maybe we'll make this a double sliding door just for some variety. It might interfere with the other door in the model. So let's keep it at, yeah, that's fine. We can just move where our door is. We'll say our door is here instead. All right. So this is going to just spawn a door right in the middle of nothing. If you want to make things more accurate, typically a door would have a frame to it. So you can use the wall tool again to create a frame for your door. So I'm going to start by clicking on the door vertex and then add another wall. I'll just have something like this for now. So again, I'll create another frame for the doors here, for the second door. This is just to improve the visual appeal of things. All right, so you should be able to go back and hit save. And now we should have a very basic site with a floor, a few walls, and a couple of doors. So if we jump back to our ROSject, we should have some commands to sort of convert this annotated 2D drawing into a 3D world that we can simulate in Gazebo. And behind the scenes, when you're, let's run this callcon build command, and then let's talk about what's happening. So I've copied these commands from terminal 1. I'm going to go back to my terminal window, and I'm going to paste these commands in here and hit enter. So what this is doing is it's building the workspace, and specifically when building the maps package. So if we go back to our code editor, and if we look at the maps package, ROScon Maps, so this is where our building YAML file, which contains our annotations, is located. And if we look at the cmake lists.txt of this package, so this has some commands for our build tool, basically commands that should run at build time. What we're saying is, okay, when you're building this package, make sure to run these tools. We have RMF building map tools, and you should see building map. It has 2 executables, building map generator and building map downloader. So what it's doing when you build this package is it internally runs these tools, and it passes in all the building YAML files that it can find within this package. So we're sort of automating running certain tools, or we're abstracting it away from the process. It's helpful when you have to keep rebuilding stuff. If you're doing a one-off build, you could just run these commands manually from a terminal, but it's just nice to have it part of the automation this way. So while that's building, let's go ahead and get the next set of commands prepared. So I'm going to go back to my Jupyter notebook. There are some commands for the second terminal. And it's important to run this from a separate terminal and not the same. We don't want to be mixing the terminal we're building in and the terminal that we're running from. So I'm going to go back to the terminal window. You might notice that the first couple of times, I should say the first time you're building this workspace, it's going to take a while to build the maps package. This is because it's trying to download certain 3D assets from Fuel. And let me talk about Fuel really quickly while this is building. For those of you who are not aware, we have a repository or a public collection of 3D assets. You can go to app.gazebosim.org/fuel, and you will be able to find a whole bunch of models here that both the community as well as OSRF has uploaded. And if you have a model you want to host, this is a great spot to host it as well. So you can go into collections. So these are groupings, 2 different for models themselves. And then you should be able to find the Open Robotics hospital collection. And this is a collection that came out of the Open-RMF project. So let's try to find that. Maybe we can search for it. That's searching for all the models. Okay, let's try to find the collection itself. All right, so here it is. So these are a whole bunch of models that were supported by the Open-RMF project. And some of them may be hospital-centric, but you can also find models that you can generally reuse for various other facilities as well. But again, we have several other of these collections that you can leverage on. We have airport spaces, office spaces, etc. And just feel free to spend some time going over Fuel to find your models. Okay, jumping back to the ROSject. So our workspace has finished building. And then I'm going to open up a new terminal and paste the second set of commands here. So here we're sort of launching the world that we just annotated. And this is going to hopefully run a gazebo simulation of the annotated 2D space from the floor plan. So again, once I run this command, it's going to launch in the GUI window. I'm going to switch to that tab here. And just give it a moment to load up. And there you go. This is what we had annotated in Traffic Editor. So you can see that the, oops. All right, so you should be able to see these walls and the floor polygon that we drew first. So it's slightly larger than the perimeter of the walls. We then defined certain walls, and then we also drew in a couple of doors in there. So you should be able to see these two types of doors and some empty space. All right, so I hope everyone's able to follow along thus far. You should also see this ARVIS window that opens up. If not, don't worry about it. We'll come back to this later. All right, I'm going to jump back to Traffic Editor and our ROSject project. So, I didn't go into some of these details, but you can also define sort of the angle that the door should swing through. So by default, it's 90 degrees. If you want your door to swing greater than that, you can also configure that. We talked about the direction. And then you can also vary the ratio if you'd like. If one of your doors is larger than the other, that's also something that's possible to configure. All right, next up, furniture. So this is where the process becomes highly creative, and it gets a lot of fun. This is one of my favorite things to do. So I'm going to go back to the Traffic Editor window here. And Traffic Editor allows you to quickly add these model thumbnails. And these thumbnails are basically 3D objects, a top view of them that represent certain models that you may find in your facility. So again, these models, we get them from Fuel. So if you see something that's not here, feel free to push that to Fuel, and you should be able to add a thumbnail for that. And using that thumbnail, you can add it to the floor plan here. So there's a whole bunch of thumbnails that are readily available. Feel free to go through each of these at your own pace. And then really flex your creative juices here and how you want to annotate the space. But here you can see the floor plan mentions that there are some tables and chairs. So I'm going to quickly add some of these tables. Don't worry about the rotation for now. Just going to arbitrarily place some of these tables. And then I can hit Escape to exit out of the placing of a model. And now we can rotate these models. You should see another icon here to rotate. Short key is R. So once I have that selected, I should be able to just rotate these tables. Maybe you have a table that's at 45 degrees or whatever, that's also fine. If you want it to snap to a certain angle, I think you should be able to hold Shift to snap to every 15 or 45 degrees or something like that. All right, let me go ahead and maybe add some chairs. Yeah, we have some really big models here. All right, so I see a desk chair. We have a whole bunch of Other chairs, let's see, let's try to find a more appropriate chair for a workshop. Office chair sounds good. So let's just add a single chair per desk. For now, it's up to you how you want to do this. Then I'm going to rotate these chairs. Ricardo, in the meanwhile, could I check with you how we're doing on time?
He cannot hear me. Can you hear me?
I can hear you now, yeah.
Oh, yeah. Sorry. Can you repeat, please?
How are we doing on time?
Oh, yes. So we are keeping this in time. You are 10 minutes to go.
All right, thank you. All right, 10 minutes to go. We've added some models here. Let's rerun those commands to build the 3D environments. I'm going to jump back to the ROSject, open up the terminal. This is the terminal where we ran the simulation. I'm going to click Control-C to exit that. I'm going to switch to the other terminal where we built our workspace. I'm going to run the same command again. And it's going to rebuild that the map that we just annotated. So hopefully what it does now is it recognizes that the map has changed. We've added in a few different models, and that building map generator is now going to download these models from Fuel when we do the build. And depending on the speed of your internet and your bandwidth, the download speed may vary. So that's what's taking a while to build a maps package. So fortunately, this was done pretty quickly. I'm going to switch over to the other terminal and launch the same world again. Switching tabs to the GUI window. And now you can see that, yeah, in addition to the walls and the floor, we also have these models that have been spawned exactly where we told them or annotated them in that 2D floor plan. So again, in the interest of time, we're going to move on. But typically when we're building these environments, we try to make them as close to reality as possible. And this really helps, especially if you want to simulate things like the navigation stack, and you want your LiDARs to hit obstacles where they are in the real world. So in those kind of scenarios, it's worth it to spend some time in making these environments match reality as closely as possible. All right, so in the interest of time, let's jump back to the ROSject. The next thing we're going to do, and this is where the robotics side of things comes in, is we're going to use Traffic Editor to define semantics of where robots can move. So what are the traversable spaces for these robots? And along with that, we're also going to spawn some robots in the simulation world. So I'm going to go back to the GUI and open up Traffic Editor. All right. So now if you go into the toolbox here, the levels toolbox, you should be able to switch to graphs. So here we have up to 9 different graphs that we can define. A graph is basically a set of lanes that a certain robot can travel along, or I should say a certain fleet. So you can reuse graphs across different fleets, or you can define a separate graph for each fleet. So to start drawing these traffic lanes, we can click on Add Lane from the toolbox on top. The short key is L. And I want to emphasize that here we're using lanes, but RMF is constantly evolving. We're now getting to a point where we don't need to define these sort of linear lanes that robots have to move along. We're moving towards a direction where we rely on free space planning. So you can just define bounding areas of, okay, this is traversable area, this is not. But for this demonstration, let's stick to these semantics here. So I'm just going to arbitrarily draw some lanes. Again, this is where your creativity can come in, or maybe as a facility owner, you know certain areas that your robots can move towards and cannot move towards. And these kind of lanes basically just define where your robots can move. Yeah, we had a door. So let's actually have one of these lanes pass through a door. Oops. All right, I'll just have it stop here. Typically, you want to be mindful of resting spots for robots. So you don't want to have a waypoint like this signify a location that a robot can go to, because it's sort of in the middle of the way of other robots. This will be solved by the reservation system we plan to introduce in RMF, where robots can sort of reserve certain waypoints for them. But in the meanwhile, at least for the purpose of this workshop, if we want a robot to sort of pause or stay at a certain spot, let's just create a leaf node. So a leaf node is something like this. It just has a single lane going towards it. There are no other lanes that emanate from the exit vertex. All right, sorry, it's a bit laggy here. All right. So now we've sort of defined these lanes. We can annotate certain properties of certain waypoints. So let's look at this waypoint here. When I click on the waypoint, this property box opens up. And let's fill out certain properties here. So if you go back to the ROSject, one of these slides gives us some properties to fill up. And we'll be annotating two separate waypoints here. So we'll be giving it these properties. So I'm going to go back here. Click on this waypoint. I'm going to give it a name. So I said the name should be charger_1. Let's just assume this is where the robot should charge. And then I'm going to give it a property is charger, and then true. And let's give it some more properties. So these are properties related to traffic management. And now let's give it some properties for simulation alone. So this is to just tell Gazebo to spawn a robot here. This is just to simplify, again, the process of creating these 3D worlds. So spawn robot type, I'm going to call that tiny robot. And this tiny robot, this string just matches the name of the robot model that we have on Fuel. If you have your own robot with its own name, go ahead and give it that name. We also have to give this specific instance of the robot a unique name. So let's just call that tiny robot 1. And okay, that should be good. Let's spawn another robot just for fun. Maybe here. So I'll call this charger 2. On robot type, tiny robot, and then let's give it another unique name. Tiny robot 2. All right. And let's also give some of these waypoints some names. Just for fun, I'm going to extend this lane here and then maybe call this P0. That's the name of a waypoint that the robot can move towards. And then let's give this P1 for point 1 maybe. Let's give this P2. And again, I encourage you to spend more time on really thinking about how these lanes should be drafted. One thing I forgot to mention is right now these lanes are given a bidirectional property, which means the robot can move both upwards and downwards through the lane. If you'd like to constrain that, you can change the bidirectionality from true to false. The short key is also just pressing the B button. So now you'll see the arrow that depicts that, okay, then the robot can only move in this direction along this lane. So let's do that. Let's say that all the robots should only move down through here. And then if they want to move up, they should sort of move through this door. So there's two different doors here. All right, I'm going to save. Typically, you don't have to define like a single lane like this for robots to move through. You can define like through the same door, you can have a lane that's going up and down. You can separate them if you'd like. If you have sort of narrow corridors like this, you can also sort of define lanes like this, where, you know, should only go up this way and then come back down this way. So that's something that you can also do to sort of manage the traffic in your facility. All right, so next up, we are going to go back to our ROSject. We have to make one. I want to quickly talk about fleet adapters. I know we're running out of time, but
2
probably
minutes.
just
Yes.
2 minutes here. Yeah. So if you go into our workspace, you should be able to see. Let's see ROScon demos. All right, it's called TurtleBot here, but we're defining these robots as tiny robots. So we need to give our fleet adapter some information about our robots. So spend some time going through this information and define certain kinematic properties of our robots that we can use to kind of model how fast the robot takes to move. But then in this configuration here, we're saying we have 2 robots that we want to manage in this fleet. There's Tiny Robot 1, Tiny Robot 2. It's important to have these names match the names that we gave in Traffic Editor. And here under start, it says charger 3. We didn't define charger 3 previously, so sorry about the confusion. Let's just change this to charger 1 in both locations. So this just says that, okay, this robot's assigned this charger, for example. The rest should be fine. I'm going to jump back to my terminal here. Quickly rebuild. And while that's rebuilding, let's take a look at what we have to do next. We're just going to send some commands to the robots to move around. And here we're sort of sending 2 commands here. We're asking the robot to do a patrol type of task, which is just to move between waypoints. And you can change these waypoints. It says P2, P4, P6 here. Maybe you call them P0, P1, P2. So whatever you call them, feel free to change it to that. And yeah, copy that out. Let's jump back to our ROSject window. The build is complete. Now we can launch. If I jump back to the GUI window, we should have ARVIS and Gazebo open. And now you can see the robots in Gazebo here. If we open up ARVIS, you'll see that in the visualization, you also have the current positions of the robots now. So again, these are the fleet adapters that are getting data from the robots, and they're telling RMF this is where my robot is at the moment currently. So let's go back to the terminal and let's try to send out some tasks. So again, copy these commands. And then let's send some robots out. Again, I had some waypoints P0 and maybe P2. And then once I send these commands out, you can see that now this robot has an intention. It has an itinerary of going to this location and going to a second location. It's going to pass through a certain door. While that's moving, let's quickly send maybe another command from our terminal too. So I'm going to jump back here and then maybe change that to P2 to P1 maybe. So hopefully this dispatches out another robot. And again, behind the scenes, RMF is working together with the fleet adapters to figure out which robots can do these tasks and appropriately move these robots to, okay, here we go. So I'm just trying to rearrange these windows. All right, so let's take a look at what happens when the robot goes through this door. And a few more paths along the way. Hopefully you can still see the robot moving. And a whole bunch of waypoints this way. So this is a very simplistic task that we're dispatching. We can also compose much more complicated tasks. And as you can see here, the robot's ready to go through this door, and RMF is aware of that. It opens the door for the robot, and the robot's able to go through the door. Once it knows that the robot's gone through the door, it will close the door again. And in the background, you can sort of see the other robot moving out as well. So I encourage everyone to kind of play around with defining these traffic rules, maybe building more complex environments, and also sending different commands to OpenRMF to sort of see how OpenRMF manages traffic. So I've sent out a few requests here, and now the robots will have potential conflicts along the way, and OpenRMF should be able to resolve them by asking robots to take a different path or maybe wait at a path until the second robot passes. There's a lot more to cover. I encourage everyone to also look at these ROScon slides and kind of try out some of the other stuff in them. But for now, thank you very much for listening. And I hope this helps your journey in using and deploying OpenRMF. Thank you.
Excellent presentation. Thank you very much, Yadunund.
Thank you. I'm proud for Yadunund. Great. Okay, so now let's have some questions. And dear attendees, please now go to the section Q&A tab and put your question there. We are going to pick the most voted question to ask the speaker.
Yes, and then in the meantime that we are waiting for your questions, let me ask you one myself, Yadunund. So you have shown this amazing software, which is the OpenRMF, and this demonstration, which is working right now, is awesome. But my question is, does this software work only with ROS-based robots?
Yeah, it's a great question, Ricardo, and we get this all the time. And the short answer is no. OpenRMF is designed agnostic of ROS. I say this with regards to communicating with devices, specifically robots. So your robot internally may use ROS1, it could use ROS2. Maybe it exposes the topics, the ROS topics for external users, maybe it doesn't. So for example, you have the MIR robot, it uses ROS internally, but users can only interface with the robot through a REST API or maybe a WebSocket API. And that's totally okay. The point is you'll be able to write your fleet adapter such that whatever protocol your robot uses to communicate or ask it to move somewhere, ask it to stop, get information from the robot, you can implement your adapter such that it talks to the robot using that specific protocol. You get that information back, and then the Fleet Adapter API will automatically convert that to a ROS2 message and send it to the other RMF nodes that do the traffic management. So your robot can be ROS1, ROS2, can expose REST API, WebSocket, OPC UA, EtherCAT, whatever you want. That's totally okay. You should be able to integrate any device with OpenRMF.
Excellent, excellent. Then that's very important because many companies, they are building robots that are not based in ROS, so OpenRMF is open to all those systems. Let me ask you some questions. One, the most voted here from the audience, that says, so the waypoint define will be fed to the nav2 library for the robot to navigate, or this is another library for navigating the robot? And how about the cost map? I think that he means, what about external obstacles that appear in the path?
Yeah, that's a great question. I didn't have time to emphasize this, but the navigation stack these robots are using in simulation is a very simplistic, I think there's a slide somewhere else, but I'll just talk about it. It's a very simplistic navigation stack. So we have our own navigation plugin called Slot Car, and it basically guides our robots in simulation along these straight line paths. It has no sense of the obstacles or the environments around it. It just quickly calculates a trajectory for a robot to move from one waypoint to another. But I want to emphasize that this is purely for the simulation we are running now. If you want to run a simulation with a full navigation stack, that is totally possible, right? We do this way because we want to save compute resources. When we run RMF, we typically have 10, 20, like many robots running. And it's hard to have the compute resources to simulate all of the robots if each of them have a navigation stack. So since we're more focused on coordination and orchestration between robots, we assume that whatever navigation stack the robot has, the real robot, that will be in charge of moving the robot from one waypoint to another. But what RMF is doing is saying, okay, now you can leave this waypoint and go to the next waypoint. And along the way, you tell me where you are. If something changes, if another robot gets delayed or you're taking longer than what you told me, I will give you a new path. And now your responsibility is go through these waypoints again. How you go through them, that's up to your navigation stack. So we've had several other fleet adapters that we've integrated here. So again, in this ROScon deck, we had a demo of, let's kind of skim
which is included in the ROSject, right?
It's included in the ROS check too, so you should be able to try that out. Let's see. There's a lot of information here. Yeah, so we can simulate a full nav1, nav2 stack as well. And here you have OpenRMF sort of guiding robots through these waypoints. But OpenRMF is just saying, go to this waypoint next. But the nav stack is using its own sensor models and cost map information to plan the motion of the robot.
Excellent. Yes, that's something, this point is a very good point. That's something that when we started to work with OpenRMF also we're very curious about. And then you clarify very well. So in this simulation, it's not using navigation in order to move the robot, but it is using the plugin, what's the name you mentioned?
Yeah, that's right.
Yes.
It's a very simplistic navigation plugin.
Yes, exactly, which is taking gazebo information and sending the robot around. But you can use navigation in the simulation, and if you have this in the real robot, then you cannot use the plugin because that plugin is only for the simulation. You need to use the navigation system.
Exactly.
Okay, great. One final question, which is very related to this one. It's from Edgar Carrasco, that he says that regarding the lanes, you have the robots on a line going up and another robot, I suppose, is going down, where they are restricted to those lanes. So I think that he means how to manage conflicts between the robots that are moving in two lanes that are going to... One robot is in the same lane as another one, because maybe you have in this image that you have now on the screen, there is a very large path at the top that starts at the top and then goes to the bottom. So maybe one robot is at the top moving in one sense in one direction, and there is another one moving in the other direction. So what happened?
That's totally fine. OpenRMF will be able to handle these type of situations. So there's two things here, right? Can two or more robots be on the same lane? Yes, they can. If they're going in opposite ways, hopefully that scenario doesn't start. That does not happen to begin with, because you've defined your traffic lanes in a way that, well, let's assume, okay, let me explain it this way. So if you've had two or more robots coming down the same lane, that means RMF has already failed, because the point of RMF is to avoid those situations. So hopefully that doesn't happen to begin with as well.
Exactly.
Because that's the deadlock situation we talked about before. That's one that shouldn't happen, because maybe the robot will be asked to just wait here or wait somewhere else so that this lane is free for it.
Exactly.
But you can also define these lanes intelligently, so you can have these kind of waiting points. So if a robot down this lane, RMF will ask you to kind of go here and wait, while the robot coming this way will have way to move forward.
Okay.
So that should be possible. And here you can kind of give the same nav graph to two or more fleets, but if you want to kind of have another nav graph for a second fleet, you can define a second nav graph, something like this. And then that's given a different color. And then you can say your fleet A can only use the green lines, fleet B can use the blue lines.
Excellent.
Or you can have fleet A and B both use the green lines. That's also fine.
Exactly. So because each fleet has a different goal and objective, different robots and so on. So we have a lot of more questions here, but we have run out of time. We have so many questions. So then anyway, thank you very much, Yadunund, for that excellent presentation. Thank you.
All right. Thank you, everyone.
Thanks,
Ricardo.
Yadunund.
Thanks, Construct.
Okay, dear attendees, now you should see a small box appear in the chat where you can rate the speaker. So please take a moment to read this speech by Yadunund Vijay, as we are going to announce the best speaker at the end of the conference. Okay, then let's continue the conference.
And yeah, we'd like to ask you, so after this first presentation, so how do you feel, the audience there? So do you start to feel this super motivation to become a super ROS developer and save the future? What do you think? Let us know on the chat.
Yeah.
Well, okay, so before we move into the next speech, let me remind you that you have to start opening now the second ROSject. This is the ROS project for the next speaker. You can see the button here, underneath here. Well, it depends on the Docs tab, probably.
Yes. Get ready, and then while we're waiting the next speaker getting ready, now let's have some fun challenges.
Oh, great.
Yeah.
So what is this?
So now we're going to do a prize quiz. The winner is going to get an ROS developer t-shirt, just like this one, or those one, and a coffee mug. Yeah, which is sponsored by the Robotics Developer Masterclass, a program designed to convert you into a robotic developer ready to work in 6 months.
Great. And how does it work? So we are going to show a video which lasts for several minutes about this sponsor. Then at the end of the video, it's going to be a question that can be answered by watching the video. Then the first person that answers correctly answers this question on the chat will be the winner of the t-shirt and the map.
Coffee mug.
Okay? So
Good luck.
let's go with the video.